Good afternoon, everybody. Dan, Justin, and myself are really excited to be here this afternoon to talk to you today about Twitter's next generation monitoring and alerting system. So the goals of this 2-year-long project were to improve reliability, to simplify the user experience, and to empower human reasoning. Over the next half hour, we'll share what we accomplished, as well as especially what we learned over the course of those 2 years. Hopefully, this will give you some food for thought as you choose amongst the many monitoring and alerting tools that we've talked about over the past few days. Or perhaps build your own. We won't deep dive into our architecture here, but we'd be happy to discuss it afterwards. Please meet us outside or in our Slack channel. But first, we'll introduce ourselves. So I'm Megan, and along with Dan and Justin, I joined the observability team about 3 years ago. When I started, I was very interested in visualization, but since then, I've become interested in learning more about the user experience of alerting, as well as the challenges of implementing that user experience at scale.
And I'm Dan. During my time on the team, I worked on alerting systems, old and new, but I'm also interested in distributed systems and computation theory and engineering systems that make other engineers' lives easier. I recently joined Google, but these guys were nice enough to let me present with them anyways.
And I'm Justin. I've had a lot of fun working on lots of different parts of Twitter's monitoring stack, but most of my time has been spent working on the alerting service and the visualization front end. Oops. Sorry, guys. So my favorite part about working on this team is actually empowering our users to do their work better. Along those same lines, I'm going to empower Dan and Megan to do their work better by, talking about all the old stuff and saving the fun new stuff for them. So before we dive into the alerting system, I'll talk really briefly about what our team does in the context of Twitter engineering. So the mission of the observability team at Twitter is to provide a scalable, robust, and real-time monitoring infrastructure to our users who are other Twitter dev teams. So practically, this means we provide a means for our users to write, alert on, and visualize their metrics. So the observability team isn't directly responsible for the monitoring of all of Twitter's production services, but rather we make the platform and product that allows teams to do this themselves. So you can say that we're not the watchers on the wall, but rather we build and maintain the wall. So the observability stack looks something like this. I know Katie showed a similar diagram earlier this week, but Twitter runs in multiple zones, which are collections of co-located servers that run within a network, and a stack like this exists in each of those zones. So the lifecycle of a metric begins on the bottom of the screen, where users export metrics, which are all doubles, as JSON on HTTP endpoints on their services. Collection agents sit alongside our users' service instances and pull those endpoints every minute. So they send the metrics to our time series database, which is backed by the Manhattan Key Value Store, and from there the metrics are served to our alerting and visualization services. So again, most of this talk is centered around the alerting service, which is just one small part of this big diagram. But if you're curious about the rest of it, we recently published a blog post a few months ago called Observability at Twitter. I think if you Google it, the first result is the older 2013 version, but the newer one should be right under that. Cool, so now let's talk about the old alerting system we had, what it did well, and why we ultimately felt it needed to be replaced. But first, a few words on scale. In the time since the three of us joined the team, which is about 3 years ago, the number of metrics written to us increased from about 300 million per minute to a peak of about 4.3 billion per minute before we freaked out and asked people to reduce their metrics. I think currently we do about 3.5 billion, which is right around there, yeah. So correspondingly, this increase in writes correlated with an increase in reads. So in its final days, the old alerting system handled 25,000 alerts, which together contained about 3 million monitors running each minute. And with this increased scale and use, the old alerting system began to demonstrate a few shortcomings. So we're going to frame those issues for you in the context of the 2 different ways that users interact with our platform. The first is the process of writing and maintaining alert and dashboard configurations, and the second is the way that our users interact with our alerting system while on call. So first, alert configurations. So in the old alerting system, we had a pretty straightforward object hierarchy for our alerts. Each alert contained n rules, each of which had m monitors. So a rule is basically a query to the time series database, and a monitor is a predicate applied to a single time series. So alert config files were stored in Git and uploaded to our alerting system via a command line interface. So what was good about this? First, it had a pretty straightforward, simple config language. Second, over the years, a lot of configs made their way into Git, so there were plenty of examples to look at if you were trying to write a new alert. And third, you could quickly write new configs, push them to Git, and upload them to our system. So then what was bad about it? Well, the config language is maybe too simple. The large body of existing examples suffered from bit rot and lack of ownership. And third, we made it really easy to write, commit, and push broken configs. So the config language itself was a JSON-ish, but not really domain-specific language, and it was pretty straightforward, but it was clearly not designed with templating, shareability, or reuse in mind. So to get around this, we ended up stapling on Mustache on top of it to allow some kind of templating, but it never really felt like a complete solution, and even with it, programmatic generation of configs was still pretty difficult. So to get around that, many teams created their own custom alert generation workflows using complicated scripts and templating, leading to a fragmentation of workflows. Additionally, ownership of configs was a problem, and sometimes you'd see an alert or template in the repo that you wanted to use or pull into your monitoring, but you weren't sure if you could safely do so. You'd see a file like this, and obviously your first question would be, does the farming team even plant cherries anymore? I thought they were deprecated. And then you'd git blame the file and ask the author about it, but you'd find out that they didn't work there anymore, and that was bad. So the number of orphaned and unmaintained configurations became an issue. These configs also suffered from a lack of validation. So neither at creation time nor at upload time were the configs validated for correctness or best practices. So we made it really easy for our users to get up and running fast. You could probably go from a blank editor to a running alert in about 2 or 3 minutes, but we didn't make enough of an effort to help them do it correctly. And finally, this is kind of a subtle one, but another configuration shortcoming was that alert configs were completely disjoint from dashboard configs, which were written in a Ruby DSL. And it seems kind of obvious in hindsight, but we realized that it was redundant to require users to maintain separate configurations for these objects when the two of them often operated on the exact same data. This, of course, isn't an absolute rule, but we observed that if your metric is important enough that you want to alert on it, you probably also want to chart it as well. So when the configs were kept separate, a user might add a helpful new metric to their alert, but forget to add it to their dashboard. So it's possible that a user could be alerted for a metric, but be unable to see it in their dashboard when they went to diagnose. Or even worse, a user might accidentally be made aware of an issue in their service by randomly browsing their dashboard instead of having been alerted by it. So once users had alerts uploaded to the system, they faced a new set of challenges being on call and interacting with the alerts. So as mentioned earlier, the old alerting system was one cluster per zone, and this meant it only knew about data from its own zone. Therefore, when that zone would go into a degraded state due to something like a network issue, it was possible that the alerting service would become impacted as well, resulting in missed alerts. And apparently, an inability to alert during service outages is not a desired property in an alerting service. So to get around this, teams would put alerts in multiple zones for redundancy, but they quickly found out that this resulted in redundancy. So in order to protect themselves from zone-level failures, they had to suffer being alerted multiple times during normal operation. Beyond this, there were 2 other issues that could lead to faulty alerting, and the first was that the old system didn't have the best isolation properties. So an alert by a bad actor with 1 or more excessively expensive queries could easily delay the execution of all the alerts running on a particular shard of our alerting service. The second was that deploys were impactful. Alert executions didn't happen during deploys, and those executions were never retried, even after the system came back online. So this led to users losing visibility during that period and potentially not being alerted about issues in their services. Deploys didn't usually last longer than 5 or 10 minutes, but still it didn't feel good for us to cut off all alerting whenever we wanted to deploy new features or bug fixes. So now I'll hand things back to Megan to talk about how we went about solving some of these things.
Thanks so much, Justin. So how did we set out to solve these problems? We created a new system that would scale as Twitter grows. We wanted to improve the configuration experience that Justin described, and we wanted to reduce lost visibility due to system issues. So what did we end up doing? Well, the first issue we tackled was the configuration story, and we wanted to simplify configuration to make it much easier to create, tweak, and maintain alerts as well as dashboards. But simplification also needed to be balanced against the need for expressiveness and power, because for us, some of our users are happy with a one-click solution, but we have many power users who really need a programmatic solution to configuration. The main way we achieved simplification was actually by combining the configurations for alerts and dashboards. So now there's absolutely no chance that an alert or dashboard configurations will diverge. An alert is simply a predicate that's placed upon data that you're already looking at on your dashboards. So by co-locating these alerts and dashboards, users no longer need to jump between tooling in order to diagnose issues. All of the relevant information is in one place, meaning faster remediations and happier on calls. Next, we reduced cargo colting by making configurations shareable. So the new configurations are written in Python rather than that janky DSL, and this gives users immense flexibility. It makes it simple for users to follow best practices. In order to do that, we created a shared library that could be easily imported. Now, creating a new configuration is as simple as importing and calling a suite of library modules. For example, if you want to monitor the JVM, you don't really need an in-depth understanding of how to monitor the JVM. You can simply import the configuration for the JVM module, and you're good to go. Choosing Python for our configurations also let us test these libraries and the user's configs. So basic tests are created automatically now for every single config, and they must pass before the configs can be merged. We also layered on top of this a more robust server-side invalidation portion, which protects users from common mistakes. For example, following best practices, or perhaps having too expensive of queries and bringing down other users. Together, these choices have resulted in higher quality and better maintained configurations. So we were improving our configurations, and that was all going well, but we were only halfway there. Without a more reliable alerting service, users still can't trust in their alerts or in the health of their systems. To fix this issue, we began by solving that single zone failure problem. This meant that alerts couldn't be zone local as they were in the old system. Instead, we needed alerts to rebalance during zone failures to a healthy zone. So with this new multi-zone alerting system, users no longer need to deploy their alerts to all zones and be double alerted or lose visibility when a zone is failing. The next problem was dropped evaluations. So now, when an alerting node fails, the new system keeps track of the last successful evaluation point, and when an alert is balanced to a new node, it restarts evaluation from that point. Not only does this facilitate our deploys, so you don't have outages, but it also means that alerts being rebalanced between zones does not cause a gap in evaluation. So together, all of these things mean that users no longer lose visibility, and that means that they can put more trust in the alerting system. Finally, the new architecture of each alerts means that each alert's execution is scheduled fairly. This means that expensive alerts don't starve other alerts. It has allowed us to improve the alerting system's time to detect by about 30%, from 2.5 minutes to 1.75 minutes. And again, this really means that users are going to get alerted faster and be able to solve problems quicker for the business. So I've described a lot of things, but what does the architecture actually look like? Now, there's going to be a lot of lines and boxes on this slide, and I'm not going to dig into each one of them. If you want to discuss the architecture in more detail, we'd be happy to do that after the talk or on our Slack channel. But I am going to walk you through like 3 of the basic moving parts. So the first one is that we have a balancer that assigns alerts to logical shards and rebalances those shards when physical nodes go down. For instance, during a deploy or a zone failure. Each minute, the system checkpoints the most recent successful evaluation, and on startup, resumes evaluation from that point. So this system is designed for graceful degradation. Failures have a limited scope. For example, if that sharding system goes down, work allocation will stop, but it won't actually affect the evaluation of alerts. Or perhaps if the history database was to go away, we wouldn't be writing history data anymore, but it wouldn't impact any of the other portions of the alert evaluation. And again, we'd be happy to discuss this architecture in more detail. If you have any questions, come find us after the talk. So with these improvements to reliability and configuration, we created a more reliable and less frustrating experience for our users. But monitoring is more than just the sum of its parts. The end goal is to help users actually solve problems. So there are a couple other things that we did, and the goal of those was to help solve the problems that come from complex distributed systems interactions. As we've heard before, monitoring isn't unit testing, it's closer to integration testing. And we really needed to make it trivial to reason about the system as a whole and to bring together relevant signals from across the stack. So we began thinking of a way to provide this, and we set it on 3 different types of context. So the first one is global context, peer context, and then local context. And what this meant for us was that globally, users need to know about ongoing changes like site-wide failovers or issues with backbone components like the network. The next thing that they needed to know about was the health of their direct dependencies. For example, is their storage layer struggling? Or is their client not sending them any requests? And finally, they need to know about recent changes to their own systems, such as deploys. By bringing these signals together, we were able to enable human reasoning and improve the time to root cause issues. But there is one more step in responding to alerts. Once you've root caused an issue, you're not done. You need to actually remediate that issue. So we needed to make it trivial to respond to alerts once you determined what the problem was. And we accomplished this by including descriptions, contacts, escalations, and runbooks right in the alert UI. This makes it simple for you to understand what you're looking at. You can escalate to someone else if necessary, and you can follow concrete runbook steps, like the ones that Katie described on Monday. So altogether, these improvements, the goal of these improvements was to empower human reasoning, to bring those signals to the right place. And now I'd like to hand it over to Dan to talk to you about a few of the lessons that we learned.
Thanks, Megan. So now comes the part where we come clean and tell you all about the parts that haven't gone as smoothly as you might think. Problems always come up when making a new project, but they tend to magically disappear when a presentation is being prepared. So that's a shame because a lot of the valuable knowledge comes from those problems and the solutions that people figure out after a lot of hard work. So a big challenge to writing the alerting system was making it distributed. From the beginning, we knew that it would have to be so. We wanted availability numbers that aren't possible without distribution. And we needed this new system to scale horizontally to at least another order of magnitude relative to the previous system. Well, as we've heard from previous speakers, distributed systems are hard to get right, even though exactly how hard depends on the problem. In our case, the system has a considerable amount of state, which is hard to keep consistent. It aggregates data from multiple sources, which can make the logic pretty convoluted. And it also computes data in real time, which requires that it know how to deal with delayed data and excess load. Well, as you could have predicted, distributing the system was the cause of a number of challenges. I'll focus on one in particular, but first, some context. As you know, any system that wants to parallelize work needs some way to divide that work into smaller pieces and assign those pieces to workers. That's called sharding. And how you do that is actually one of the key decisions when designing a distributed system. Here, the work is evaluating alerting rules every so often and taking action based upon that. We chose to shard the alerts by ID and assign them to workers dynamically. That's a pretty intuitive way of doing things, but we could have made quite different choices. Secondly, our implementation relies on existing tools as much as is safe for a monitoring system. It depends on Zookeeper for maintaining consensus, on Manhattan, Twitter's key value database for keeping state, and on Aurora for orchestrating those instances. Designing a distributed system from scratch is a daunting task. At the beginning, all we have is a list of rough requirements, an excess of tools to tackle them, and a blank screen. Lucky for us, people have thought about many of these problems before, so we have a bunch of great advice on how to design our system. Some of that advice takes the form of principles. For example, we should come up with clean abstractions that capture the work that needs to happen. We should minimize the amount of coordination required between those abstractions to keep their interfaces simple. We should parallelize the work so we can scale the system. We should make sure that the load is distributed evenly across those machines so that we can run efficiently. We should also make these decisions quickly and ship a product in a timely fashion. We take, all of us, these principles seriously as engineers, like a code of honor that guides how we write code. If you think about it, we're kind of like knights with our own kind of chivalry that's not sexist. Well, there's one kind of knight, or one knight in particular that I want to talk about. Jaime Lannister. Jaime Lannister was a knight, maybe the best swordsman in the land. As a great knight, he had a code of honor. He took vows and he did his best to live by them. He served as personal bodyguard for the king. He loved his family. He protected the weak and was known throughout the land. Now, if you've watched Game of Thrones, you may know where I'm going with this. If you haven't watched through season 3 or read the books, then cover your ears and eyes for a moment because there's some minor spoilers coming up. I left some details out of my description of Jaime Lannister. I didn't lie. He did serve as personal bodyguard for the king until he stabbed him in the back. He did love his family so much that he fathered some kids through his sister. He was one of the best swordsmen in the land and protected the innocent until his right hand was cut off for trying to save a woman from bandits. He was known throughout the land, infamously, by the name Kingslayer. So he sounds like a kind of nasty guy, right? Well, some fans may disagree with me, but I think he's actually a pretty awesome guy. He's just been put in a lot of really difficult situations. Okay, spoilers over. Open your eyes, because you can see this. So you may be thinking, what does this have to do with monitoring? Well, just like Jaime, we have our code of honor, and we've taken our vows. In our alerting system, we have pretty intuitive abstractions, rules and rule sets, where rule set is just an alert by a different name, essentially. So we can chart along those lines, but we have a choice to make. Rules are more compact, uniform units of work. So ideally, we'd want to make the cut there and distribute along those abstractions. But if we do that, the lines cross. That would be bad. Not as bad as total protonic reversal, but it would force us to coordinate a lot between the results of rule evaluations. And that would lead to more time invested and more bugs. On the other hand, if we shard by rule set, we don't have that problem. But then we might have a hard time keeping the load distributed evenly because some rule sets may be much bigger than others. So how do we know beforehand which is the right choice? The problem I'm getting at is that designing distributed systems is a difficult situation. Sometimes it seems like all that great advice on designing them is like the first description I gave you on Jaime. It all sounds great when you leave out the details, but reality comes with a lot of complications. We can get through it, but our vows are going to take a beating. As Jaime himself said, so many vows. No matter what you're doing, you forsake one vow or the other. We have tons of great advice, but in the end, our situation may force us to choose between contradictory tips. When that happens, we have to do our research, buckle down, and take our best shot. As it turns out, the decision we made didn't come out all that bad. We chose to shard by rule set, like I said, to keep the system simple. And that means that the load is not actually spread evenly across the cluster. Some people, as it turns out, really do want to have 20 rules with 5,000 monitors in each one, and we don't partition those. So we could have implemented logic, or we could in the future implement logic to spread the load more evenly, but right now it's easier to just over-provision clusters. Still, things could have easily turned out differently. That's why we didn't want to come up here and tell you how to build your systems. There's lots of people telling you how to do that, and a lot of it is really good advice that's worth looking into. Just make sure that you also remember that it's impossible to avoid making mistakes all the time. And the next time you're spelunking through some horrible legacy project that's riddled with bugs and impossible to read, think about Jaime Lannister before you call the author Kingslayer. So system design is only one of the challenges to software engineering. Another family of challenges is how to give our users what they want. Users are the whole reason we do what we do. Whether we're designing consumer products or making infrastructure, it comes down to the fact that other people value what we're making. When designing and deploying the new alerting system, we had to work with our users extensively to support them as they migrated to it and collaborate them when that path was blocked. We found that even though it's exciting to have a lot of people using our system, sometimes supporting people can start to feel like a burden. After all, helping one user with a simple problem doesn't have the same impact as applying the same amount of time to improving the project. At the same time, some user questions really do deserve a team member's attention. So we set up multiple lines of defense to reduce the amount of time spent supporting users on known problems. The front lines are the points of interaction with users: UI, command line tools, and configuration libraries. As Megan said earlier, we wrote a comprehensive configuration validator to warn users about quirks and frequent missteps that other people would make. We made sure our command line tools usage messages were helpful, which is pretty easy to forget to do, as it turns out. We also spent almost as much time documenting our configuration templates as writing them, and explaining how to use them in the code as well as what they mean in the context of monitoring. Behind the front lines, we placed a suite of user documentation, providing deep links from UI tools and configuration libraries to relevant documentation. We tried to make sure that it covered all aspects of the new system in a friendly way, without obfuscating the useful information. For example, we provide a simple getting started guide, which everyone has nowadays, right? Another guide devoted to explaining the core concepts of the system, a guide detailing best practices to writing configurations, an FAQ, and auto-generated API docs for the shared configuration libraries. The source of the documentation lives next to the code to simplify keeping it up to date, and we try to enforce that documentation changes go into the same review as the code changes. For the third line, we have a dedicated support on-call rotation. Each week, a member of the team dedicates themselves to user support. They're attentive to the chat room and mailing list, answering questions as they come up. By focusing user questions on a single person, we reduce context switching for others on the team. That makes it easier for the team to focus on development when their expertise isn't needed for simple questions, at the cost of dramatically reducing the productivity of the on-call. Aside from day-to-day support, our interactions with users focused on migrating them to the new system. A problem we ran into is that while some people were very excited to try out the new system, a good number of others were not. They were on the hook for other important tasks that didn't line up with our roadmap. So we tried to figure out an answer to the question, how do we get people to do what we want? To start, we took the classic carrot and stick approach. To lure users to migrate, we made the new system better with higher reliability, fewer bugs, and more features in most cases. To drive people off the old system, we stopped all non-essential development on it and set deadlines for people to stop using it. That's not the whole story, though. Lots of people were excited about trying out the new system. They even started contributing to the shared libraries. But some users pushed back. A few did so because they wanted a rarely used feature that was not supported in the new system. Others because migrating was a lot of work and they had more important things to do. It was easy to feel discouraged, but doing that didn't help either of us. What did help us was to rethink our goal. Our goal was not really to get people to do what we want. It was to make Twitter better as a whole. The problem was that by thinking in terms of carrots and sticks, we implicitly cast our users as mules to be lured and driven. But as it turns out, people are really not that crazy about carrots, and they really don't appreciate being hit by sticks. So instead of looking at our users as goals that we had to meet, we had to acknowledge them as the competent individuals they are and reach a mutually beneficial compromise. Of course, that's just the start. Such a compromise usually means committing more development work and dealing with the delays in the roadmap. We certainly didn't want delays, but sometimes they are necessary, especially from the perspective of the organization as a whole. So in the end, making a good monitoring system, or any other kind of system, doesn't come down to a single thing. It's about balancing the needs of users against those of the company and the team and 1,000 other things, in search of an optimum in an incomprehensibly big problem space. The only way to get closer to that goal is to try things, learning from our successes and failures. We hope that we've helped you in that pursuit by sharing our experiences today. Thank you for taking the time to listen to what we had to say.